to Sports Tonight. I'm Emma.
And I'm Christina.
And this is our special guest, Megan.
Hi, thank you for having me.
Tonight we're going to talk about the physics of gymnastics.
And I also brought along some videos to show you too.
In preparation for doing bars, a gymnast applies a chalk powder on their hands to increase the coefficient of friction between the bar and their hands. Without the chalk, the gymnast's hands would be too slippery and would eventually slip off the bar.
The gymnast can now easily rotate around the bar.
This is the equation for angular momentum. M stands for mass, R stands for radius, V stands for velocity.
If Megan's mass stays the same throughout a trick, she'll have the same angular momentum. For example, if her radius is large, then her velocity will be small and she will move slower. If her radius is small, her velocity will be large and she will move faster.
An example of this would be if I'm doing a flip, I would tuck my knees in tighter so I could flip faster. Here are two videos. The first one has my legs in a more open position, so I flip slower. The second one, my knees are tucked in more, so I flip faster.
The equation for centripetal force is force equals mass times velocity squared divided by radius. Centripetal force is a force that acts on a body moving in a circular path and is directed toward the center around which the body is moving. In gymnastics, the centripetal force pulls the gymnast towards the bar, allowing herself to rotate. Once she releases from the bar, that force is now broken, allowing themselves to switch to the next bar. When moving toward the next bar, the gymnast moves in the direction of her linear velocity. This repeats itself when changing from bar to bar. Isaac Newton was an English physicist and mathematician, perhaps one of the most important physicists in the world. Newton was the founder of universal gravitation, the three laws of motion, and calculus, as well as creating the first reflecting telescope. The law of gravitation is the law that states any two bodies attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This law relates to gymnastics when a gymnast performs an aerial. An aerial is a rotating flip performed without your hands touching the ground. A gymnast, or any person and/or object for that matter, cannot stay in the air forever because of gravity. This causes the gymnast to land as well as her motion moving that direction.
Newton's first law states that an object in motion will stay in motion unless acted upon by an outside net force. We can see that Christina pushing me off the beam is her being the outside net force.
Newton's second law states that the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force, in the same direction, and inversely proportional to the mass of the object. The equation for this is force equals mass times acceleration. The best way to demonstrate this is by comparing it to mass. The lighter the gymnast's mass, the faster she is able to accelerate compared to a gymnast with a greater mass, even when they both exert the same amount of force.
According to Newton's third law, for every action there's an equal and opposite reaction. This means that for each interaction, there's a pair of forces acting on each other. As a gymnast releases her hands from the bars and heads towards the mat, she hurts her feet when she lands. This is because while her feet exert a force on the mat exerts an equal and opposite force onto her feet.
The impulse is force times change in time. Change in momentum is mass times the change in velocity. Impulse and the change in momentum equal each other. When the gymnast lands on a padded mat, the impulse experienced by the gymnast is longer than it would be without. So the amount of force received is less because the greater amount of time. Gravitational potential energy is PE equal to mass times gravity times height. Elastic potential energy is PE equal to half constant times change in distance squared. Kinetic energy is KE equal to half mass times velocity squared. This is me running down the vault runway with a constant kinetic energy, and it's kinetic energy because there's no outside net forces. Before the springs are fully compressed, I have more elastic potential energy than I do gravitational potential energy. While the springs are completely compressed, I have full elastic potential energy. After the springs are compressed, I lose EPE and gain GPE. While I'm flipping off the vault, I have gravitational potential energy, but I have some KE because I'm moving at a constant speed. Just to elaborate more, as the gymnast flips through the air, her kinetic energy increases as her potential gravitational energy decreases, and no energy is lost or gained.
Thank you so much for coming, Megan.
Yeah, thank you for having me. I hope now you can apply more physics to gymnastics and you learned a lot more.
Thank you so much for watching.